Greetings all. Time to talk about law of sines. So this is going to be expanding all of our trigonometry outside of the world of right triangles into the world of all of the rest of triangles out there. So in other words, we'll be able to use sine, cosine, and so on with this law, and the next one we'll talk about in the next section, with triangles that don't necessarily have right angles, right? And that's sort of a big leap there. And it comes from the fact that I can split any triangle into multiple right triangles. In this case right here, you can see I can draw what we call an altitude of a triangle. It's a line that goes from a vertex and forms a right angle with the opposite side. Here we'll call it the height. Once you form that side, you can split your triangle into two pieces. Okay, well, once that's done, I can set up a couple of basic sine ratios, right? Here, angle A is just h over b for sine, and here for angle B is h over a for his sine. But notice if I multiply by b here and multiply by a on here, both of those are equal to h, which means I can bring them together and I have this equality here. Okay, dividing both sides by b and a, I get sine of angle A divided by side A is equal to sine of angle B divided by length of side B. And if you go through that process again with the third side and the third angle, you can actually show that through the same process, angle C, the sine of angle C over the length of C is also equal to that same ratio. This is called a law of sines. So I can take any angle side pair. Now when I say angle side pair, notice it's the angle and the side opposite it on the triangle. So then any angle side pair, if I do the sine of the angle divided by the side, or actually you can do it the other way, you can do the side over the sine of the angle, as long as you do it the same way with all pairs. Okay? You'll find that all of the angle side pairs give that same ratio. And that allows us to do a sine of an angle and relate it to a length. And it doesn't have to necessarily be in a right triangle. It can be in any triangle, hence the generic big triangle up top. One of the side consequences that we see from this relationship is that we can compute the area of a triangle in an alternate way. Normally, area of a triangle is 1/2 the base times the height. In this case, my side B is the base, my height h is the altitude. But just like over here, notice that the angle C in this right triangle here, the sine ratio of him is h versus a. Sine of C is h over a, which when I multiply by a, just like we did before, I am equal to h, which I can substitute into this formula, and I get the area of the triangle is actually 1/2 BA sine capital C. Okay, so what this really means is any time you have two sides and the angle that's in between them, right? See, AB and C is the angle in between them. Anytime you have that relationship, I can compute the area of the triangle in this way, multiplying 1/2 with the two sides and then times the sine of the included angle. It must be the angle in between them too for this to work. Notice that pattern here in this one, okay? Whereas over here it's about ratios. A quick example of this is, notice if I've got a triangle with length side 13 and 24, both centimeters, and there's 100 degrees in between them, the triangle that connects those two tips, right, into there, the area of that triangle is just going to be 1/2 times 13 times 24 times the sine of the 100 degrees. And after I punched it up in the calculator, that came out to be 153.63. And it's centimeters squared, or technically that should be square centimeters, right? That's one object, not actual squaring of centimeters. And that's how much area would fit in this triangle if those were the actual measurements. First example. Someone would ask you, or the instructions would say, or be on a test or whatever, solve the triangle. And they're going to give you 3 pieces of information. And that's important. You always need at least 3 pieces of information. And by the way, that can't be just the 3 angles, because then you could scale a triangle to any size you want. Okay? Here's the first case that works with law of sines. It's what we call angle, angle, side, or angle, side, angle. One of those types, right? Here, look. Notice we have angle and an angle and a side. But it's not just any angle and any sides, right? Notice that I have big A and little a. I have big A and little a. That means I have one of my ratio pairs complete. And that's important in law of sines. Law of sines works by proportion, which means there are 4 pieces of information in any proportion, right? Top and bottom on either side. I need to have at least 3 pieces of those in a proportion to solve a proportion. And that's exactly what we've got. The A and A pair is one whole ratio. And then the angle C will also give me half of the other one. Okay? And remember, just a reminder, angles and sides are across from each other when they're in pairs, right? Okay, so I'll set up the first calculation here. We'll do it like this. 25 over sine of 57 degrees. And notice what I've done is I've put little a over sine of big A. And remember, I told you we could write the law of sines whichever way as long as you did it the same on both sides of your equal sign. Okay? And that's exactly what I'm going to do right here. I now also have little c over sine of 93 degrees. Okay? So I set it up the same on both sides. And I did this on purpose. I put the sides on top this time because I knew that I was going to be solving for the side. The things that I solve for, I tend to put in the numerator. That makes it a quicker solving process. Because notice, the sine of 93, that's one whole value. Don't separate the SIN and the 93. That doesn't make sense. But sine of 93 is a value. And I can multiply that to both sides here. If I do that, then I'll have 25 sine of 93 degrees divided by sine of 57 degrees is equal to little c. And then from here, it's just a handy dandy time saver punch and crunch, right? Make sure you're in the correct mode. I'm using degrees here, right? So I have 25 sine of 93 divided by sine of 57. And I'm getting that C is approximately 29.7, let's say 8, right? And that's measured in feet. Okay, so that's one missing piece. There's still 2 more missing pieces here, right? I'm still missing one more angle and one more side. Well, in the angle side angle or the angle side cases here, I've got 2 angles. I can easily subtract to get to the third one, because remember, the 3 angles in a triangle have to add up to be 180, right? So angle B is going to be 180 degrees minus the 93 degrees that's already used in angle C, minus the 57 degrees that's already used in angle A. So that means B is what? We have what? 87 there. And then minus 57 will give us another 30. So B is 30 degrees. Okay? now that I have that angle, I can set up another ratio with another law of sines and find the missing side B. So here's another important piece of the answer. Okay? Same setup. I have an angle, I'm missing a side. So I'll be setting up 25 over sine 57 degrees is equal to little b over the sine of big B, which is 30 degrees. Like before, I will multiply both sides by sine 30 degrees. One thing you need to notice is I use that same information again. That wasn't just an accident, and it wasn't just a me having fun thing. You want to use as much original information in every calculation you do. If I were to use this calculation here as part of the middle of this meat in here, I would have double the amount of error that I need, right? Because this is already chopped off right here. This is already approximated. So if I plug that in and use it somewhere else, then it has even more error afterwards, right? So I don't want to use this if I can avoid that, right? And just keep it as one of the answers. So I'm using original information. And the only new piece is the 30 degrees, which we could be fairly certain is high accuracy because I didn't have to chop, right? Okay, other good news about this calculator, all I have to do is hit up and change 93 into 30 because everything else is the same. So I get 14.9. Okay? So then that's considered solving the triangle, right? I had 3 pieces of information. I found the other 3 pieces of information, and it is a unique triangle. The next 2 examples, I want to illustrate another formation that requires law of sines. And that's going to be when you have 2 sides and an angle. And traditionally in high school, they like to go side-side angle. For me and for all the classes I teach, it's just more memorable if you go off the beaten path a little bit and call it the ass case, right? Angle side side. They always say avoid that because they're going to be nice and proper, and I agree with that. But when something sticks that well in your head, you know, it can help out. And this really does feel that way too, because these are the cases that have a little bit more work to them, so it feels like it's beating you down a little bit. Just a little bit though. They're not that bad. So look, notice that what I now have is one angle and 2 sides. Okay? The main difference here is I can't subtract to get another angle this time. I'm going to have to go through the long haul of calculating all the different angles and then going through and finding any of the missing sides that go with it. In this case, only one missing side, right? Okay. So first of these 2 examples, it's actually example 2, right? This example, let's start with finding one of the missing angles. Notice the pair that you have, right? Angle B, side B. I've already got one pair going. So then little c means my only other option here is I need to find angle C now. So let's set that up. Okay, so notice this time I put the signs on top, right? So I've got my thing that I'm solving for in a numerator. It's going to make it flow better when we're actually doing the solving, okay? So let's go through and actually solve for angle C. I'm going to multiply by 13. and that's equal to sine of C, right? Which means I need to undo sine. Remember, we have a specific calculation for that. It's called arc sine, okay? But I'm not just going to do just the arc sine here. I need to remember that I'm asking a generic question about sine, okay? I'm going to get a positive number for this over here. What that means is sine can actually take on a couple of values. Sine is positive in a couple of different quadrants, right? Typically, we only think of quadrant 1 because most of our triangles have acute angles. However, the way sine works, I can have some slightly obtuse angles and they'd still fit in a normal everyday triangle. I can, for example, I can have an angle that's 113 degrees or 157 degrees. I can't have an angle that's 230 degrees or anything like that. But sine is positive in a region where, quadrant 1 and 2, right? In a region where I can have some obtuse answers. So I need to consider that there's two possibilities that can both answer this particular question. Okay? So think back to your solving trig equations. Remember, there's two pieces of information. There is the fact that sine is mixed with this being positive. That's what we just talked about. I can get quadrant 1 and quadrant 2 answers. And then there's the reference angle information that will give me those two answers. So let's take a look at that, right? I'm going to have to punch it up here. Okay, so my quadrant 1 answer is going to be the same as the reference angle. C is equal to inverse sine of 13 sine 71 degrees over 19. And I'm going to call that big C number 1. Okay? So inverse sine 13 sine 71 degrees divided by 19. I get 40.3. degrees. Okay? So that's C1, right? Or what would C2 be? Well, let's think about that. If this is the quadrant 1 answer and the reference angle for this whole situation, then quadrant 2, right? The quadrant 2 answer that goes along with that particular question would just have to be 180 minus the reference angle. Right? So that would give us what? 140, but then minus 0.3 more, so 139.7 degrees. Okay, so I've got a couple of answers here. Here's what's going to happen. If you've gotten this far, then at least one of these is going to be an answer. If you were going to get no solution to this, it would have already happened right here in your calculation. You would have gotten a big calculator scream at you error. Okay? So if you've gotten this far, one of these two or both is going to work. Okay? If one of them is going to work, it's going to be the acute one. If they both work, well, then you'll just have two completely different sets, right? And that can happen. So how do we check that, you say? Easy. Find the third angle that goes with each one. I have an angle B that both scenarios are agreement with. Both of these could be different, completely different triangles. Okay? So this triangle and this triangle, they both use B equals 71 degrees. But they're different C angles, right? So if I find the third angle, angle A, capital A, right? If both of those A's come out fine, then I've actually got two different triangles that both work. Okay? So let's do that. Now that I've got two angles for each situation, right? I've got B with C1 and I've got B with C2. All I have to do is subtract from 180. Okay, so A1 is going to be equal to 180 minus B minus C1, right? Well, let's see, 71 in here, that'd be 111.3, and I'm taking that away from 180. Right here, right? 111.3. So that would give me 70, so 68.7 degrees. Right? Add it back up just to be sure. That's 1, so 69, 150. No, 140. Okay, that's right. Okay. So look, 68.7. That's an angle that I could find in a triangle. That's a good angle. Okay. How about possibility number 2, A2? That's going to be equal to 180 minus B minus C2, right? Approximately what? Well, 71 and 139. That's going to be way bigger than 200, isn't it? So if I do 180 minus B minus C, I'm going to get a negative number here. I don't really care what the number is. I can tell already that if I do this subtraction, it's going to be negative, right? So this is not possible. So it took care of itself in that case, right? That possibility isn't even one of the answers, right? Because those angles just can't add up. But this one does add up. And I've got one piece left that I haven't solved for. I've got big B, big C, big A. I've got all my angles, and I have two of the sides. I'm still missing one side, right? That would be little a. Well, I have the angle that goes with them, and I have a completed pair. We're back to the situation we were in the last problem whenever I have two angles in one side, right? So I could set up another law of sines here. That would be like this. I'll set up the law of sines, 19 versus sine 71 degrees. And that's going to be equal to the little a that I'm missing versus sine of 68.7 degrees. And I know what we said last time, try to avoid using some of those answers again and again. In here I don't have a choice, right? That's the only angle side pair that I can get. So if I multiply both sides by this sine value here, I'll have 19 sine 68.7 divided by sine 71. And that's going to give me 18.7. Inches. Okay? So the thing to note is, I could have had two triangles here, two completely different triangles, but it turned out that one of them wouldn't add up, right? So the true answer is, I've got the B, the C, right, for the original information, but I also calculated the C angle, the A angle, and the missing A side, and that makes a complete triangle that fits the original information. Okay? Now, here's another example. Okay? This example here, I want to demonstrate how it's completely possible to get nothing that works. Okay? There are certain rules in triangles that have to do with the lengths of the sides, right? If I don't have two sides that can overcome a third side, right? If they all lay flat, you don't get a triangle. So let's see what happens here when I try to set this one up. Notice I've got the pair here, right? The A and the A pair. And then I've got the C side, so I'll be looking for the C angle. So sine 49 degrees over 23 is equal to sine of the missing C angle over 31. If I multiply both sides by 31, then I have the sine of C is equal to 31 sine 49 over 23. Okay? And just like before, I'm going to do an inverse sine for one of my possibilities. I'll call it C1, right? Because remember, we had multiple possibilities going on there. Okay? If you punch this in your calculator, you'll get an error. Okay? And that's because this piece right here is greater than 1. Right? And remember, sine and cosine, as far as the ratios go, have to be trapped in between 1 and negative, or negative 1 and 1. Right? So it doesn't make sense to ask what angle gives me a sine, right, of this ratio, if that ratio ends up being greater than 1, right? Just for accuracy, let's punch it up and see just the ratio portion. 31 sine 49 divided by 23. 1.017, right? 1.017 for the ratio is bigger than 1. And that just can't happen for any angle. So if you hit the inverse sine part on top of that, the calculator is going to scream at you, no such angle. Okay? So since this is no such angle, there's no such triangle that fits the original information. One final example. Let's talk about what happens if both triangles work. And then right after this, I have a very more accurate way of showing you exactly how two triangles can actually coexist with a lot of similar information, because I'm going to get two separate solutions here from this, and they both obviously use this original information. Okay, so I'll also at the end here show you a little graph from GeoGebra how the two different triangles actually share this information and actually coexist and can both be viable solutions. Okay, but let's calculate them first. So notice I've got the big B, little b pair, right? That's screaming law of sines to me already. And then I have the side A, which means I'll be looking for angle A. So let's set that up first. I have sine 61 degrees divided by 26 is equal to sine of A divided by 29. So I'm solving for angle A, which means I'm going to multiply the 29 to both sides, right? So this one's gone. And sine of A is going to be equal to 29 sine 61 over 26. Okay? Now don't forget, I'm having the sine of an angle equals some ratio. And technically, that could have more than one answer, right? So my first answer, A1, is going to be the acute one, right? I'm going to use the reference angle, which is plain and simple, the inverse sine, right? That's technically quadrant 1, where sine is positive, right? I can do quadrants 1 and 2, so the quadrant 1 answer is going to be the reference angle, inverse sine of 29 sine 61 degrees over 26. Right? And let's see what we get when we crunch that up. Inverse sine 29, sine 61, divided by 26. I have 77.3 degrees. That's my A1 angle, right? Let me do A2 over here. That's just going to be, since it's in quadrant 2, remember, the way we find an alternate answer with when this is the reference angle, the quadrant 2 is just going to be 180 minus 77.3 degrees. That's always how we solve the quadrant 2, right? We do 180 minus the reference. That's not the same thing as taking the 180 for the 3 angles in a triangle. This is the 180 because of the way we understand solving for sine in quadrants 1 and 2. Okay, so 180 minus this, I have my A2 is going to be equal to 102.7 degrees. Right, double check me there. Right, so that's 78 plus 2 is 80. Yep, that's good. Okay, so like I said before in the last couple of examples, how do I know if both of them are going to work? Well, just continue the problem. I found an A angle. I already have a B angle. So subtract out and find the C angle that goes with them, right? Start there. So C1 is going to be equal to 180. Now this 180 is because of the triangle sum in 3 angles, right? Minus B minus A1, because that's the triangle set that I'm doing right here. Okay, so 180 minus B, right? That's going to give me. Well, let's actually add these two together. That'll be easier, right? That's 138.3. So 41.7. Right? 7 and 3 makes 42. And 19. Yeah. Okay, good. So 41.7 degrees. Okay? So obviously that fits in a triangle, right? And the only thing I would have left is to find the missing side that goes with this. I'm going to use the original information to do that. Okay? So this is part of the answer. This is part of the answer, but I need one more piece to the answer. I need the third side. So I'm going to do 26 divided by sine 61 is equal to the missing C1 side over sine of 41.7 degrees, the big C angle, right? That's just another law of sines. I multiply this sine value over here, right? That's all I'm doing. C1 is going to be equal to 26 sine 41.7 divided by sine 61 degrees. Put some approximately there, and let's crunch it. 26 sine 41.7 sine 61 19.8 centimeters. It's part of that answer there, right? Okay, so now we want to set up for this other one, right? I've already found all of the missing pieces of information over here on this triangle, which means that I have one entire solution, right? All 6 pieces of information for one entire triangle, okay? But This other one may still yet work. We haven't checked it yet. We haven't continued to see if the third angle will add out to be something useful, right? And if it does, then it's also a viable triangle. Okay? All right. So now for C2, the second possibility of angle C. 180, not because of the same reason, right? This is the 180 because of the solving the equation. This is a 180 because of three angles in a triangle. Minus B, which is the angle they share, minus A2, right? So let's see. A2 is 102.7, B is 61, so that's going to be 163.7. So 16.3, right? Let's double check it, right? That'd be 103, be 119, be 61. Okay. So notice 16.3 totally works in a triangle. Totally works, right? I have a 61, a 102.7, and a 16.3 degree angle. That can be a triangle, okay? And I've already got two of the sides to go with the information. Again, I'm only missing that third side, little c number 2, okay? So I'll solve it the same way. I have another law of sines set up. I will be setting up 26 over sine of 61 degrees. And I'm going to set that equal to little c2, right? The missing side divided by the new angle that I found, sine 16.3 degrees. I'm going to multiply this sine 16.3 to the other side. And little c2 is going to be equal to 26 sine 16.3 divided by sine 61 degrees. Let's crunch that up. Yeah, it's almost the same as that other one, isn't it? I'll just have to change the 16.3. I'm getting 8.3. centimeters. Right? Okay. So again, the thing to notice here is that I have two different sets of solutions. Okay? In other words, I have a complete triangle here using big B, little a, and then A1, big C1, little c1. I also have a completely other triangle that you can draw either on top of or even somewhere else with using big B, little a, and A2, big C2, and little c2. And it will also make a completely usable triangle. Okay? So the instructions just say solve the triangle, which means find a triangle that uses this information. Well, we found two different ones, and the information completely lines up. Both of these triangles use that original information. Okay? So, as I was saying at the beginning of this, all right, let's finish out with taking a look at what these two triangles look like, and you can see how they line up. Our original information was we were given a 61 degree angle. So let's change that. And then our two sides were 26 and 29. So the 29 is already set. I'm going to set the 26 now. And there we have it, right there. You can actually see that there's two triangles in there. And let's point out the features. The angle B right here is that original 61 degrees. And you'll notice both triangles, right, from B to C2 and B to C1. That's the two triangles that we're talking about here, right? B,
C2, and then A, and then B, C1, A. Those are the two triangles. Notice they both share this angle B, which is the original 61-degree angle. Okay? They both also have the same length, B1 and B2 here. I know they're labeled differently, but the actual lengths on B1 and B2 here, notice on the side, they're both 26, which is the original information that it's supposed to be, right? And then the other piece of information that was original was the length 29. And they both have this bottom side as one of their sides. But notice two completely different triangles, right? I have this one and this one. And look, there's the angles that we calculated, the 102.7 and the 77.3. Remember our two different A1 and A2 angles? And then over here, you have the subsequent other angles that went with them, right? The 41.7 and the 16.3 both fit here like they're supposed to. This is exactly how the two triangles would look if you were to lay one of them on top of the other. Okay, but the idea here is that you can see they are both very real triangles.